Okay, so I've drawn an object at the top of an inclined plane. The height is L, the angle is theta. All the surfaces are frictionless. The object comes down this inclined plane. It obviously speeds up, and then it travels with whatever speed it has here to here, and then the speed here starts to decrease as it goes up this incline, and we want to find the distance that it travels along this inclined plane. And I call that x. So we're in a tilted x reference system. So tilted, this is horizontal, and this is vertical, horizontal and vertical. And the final speed here will be the initial speed here, and then acceleration will slow that down, and it'll come to a stop. That will allow us to find the time, and then we'll get the distance by putting that time in. So let's find the speed v here. So that's vb, and that becomes the acceleration in this tilted horizontal direction is the component of gravity along that direction, which is g sine theta times t. So that's the ax times t, the horizontal acceleration, which is that way, and we've chosen it to be positive, but we don't have that time, and so we have to get that time from the x position, so the object starts here and it ends up there. What is that distance? That's the x distance, and that becomes, we can get that from geometry, which is that, x, right, so this is the x distance here. It's not that x distance, so let's maybe call it x1 there. x1 sine of theta is equal to L, and so x1 is equal to L over sine of theta, and so our equation is L over the sine of theta is equal to 1/2, ax t squared, and ax is g sine theta. So we have that. That's the x equation. And so t is 2L over g sine squared theta square root, and therefore we'll plug that into here, and we'll get VB equals g sine theta times that t, which is 2L over g sine squared theta square root. And that can be simplified. We have square root of 2. We have g over square root of g. That's the same thing as square root of g. We have L, and the signs cancel because square root of sine squared is just sine. It's just the sine, and we have sine here, so we get that cancels out. So we get the speed at the bottom of the inclined plane. Now that speed is the initial speed for this incline, so other incline, and we can say that the object reaches 0 speed on that incline. Right, the equation is final v, 0, equals initial v, which is the square root of 2gl, minus the acceleration times the time. And the acceleration on this incline is this way, and it's g sine of phi. Just like here it was g sine theta in magnitude. Here it's g sine phi in magnitude. But of course it's that way, and so our convention requires that we have a minus sign there, because the speed here is, we made it positive, and so we have v initial minus plus ax times t, and that equation will give us the time that it takes to come to a full stop, and therefore that is 2gl square root over g sine of phi, And now we can figure out the distance it travels here by going to the x equation for this incline, the tilted x equation. And that is, v naught t plus 1/2 ax t squared. And so the v naught is 2gl square root times t, the v naught t. The acceleration is negative g sine phi. We have t squared. We'll plug in our t that we have here into this. So we have 2gl square root times square root of 2gl over g sine of phi minus 1/2 g sine of phi times square root of 2gh over g sine phi squared, which gives us, here we have 2l over the sine of phi minus, let's see, we're squaring this, these cancel, we have 2l, sorry, we end up with the 2's cancel, so we have l over sine of phi. And so we end up with l over sine of phi as the x, as the distance traveled along here. And we can notice that we can ask how far up did it travel? What's this distance? And so that's x sine of this will get us that. And so x sine of phi, right, this is x sine of phi is just L. And so the height that it reaches on this side is the same as the initial height there. And we will see how that works from the perspective of energy conservation.